My name is Ian Centino, and I'm the director of the Global Systemic Risk Project. You all know about CITP, but just let me take this occasion to plug a little bit about the GSR. We were founded 3 years ago and now have some continuing funding to look at all the worst things that happen in the world, basically. And we wanted to start, we should have done this about 3 years ago because of almost everybody's nightmare scenario, except maybe in health, begins with some kind of internet failure or another. So in my innocence, my technological innocence, I actually asked Nick, could the internet actually fail? And he looked at me and went, lots of complicated questions. So this is what led to this wonderful panel. I'm sure you guys know both of our panelists, but let me just introduce them. First is Jen Rexford, who is the Gordon Wu Professor of Engineering and the Chair of Computer Science. And then we have Nick Feamster, who is Professor of Computer Science, and he's the Active Director for the Center for Information and Technology Policy here at Princeton. Thank you so much for agreeing to do this.
Great. Thanks. So what we're going to do is we're going to sort of divide the time into sort of two main parts for our remarks and then open it up to questions. So I'm going to start by giving a little bit of background about the internet to set the stage for understanding some of the risks inherent in the internet. And the main punchline there, to cut to the chase, is one of the things that makes the internet such a huge engine of innovation is exactly the same thing that makes it so vulnerable to all sorts of attacks. And then Nick is going to walk us through some of the recent risks that have happened, particularly with cyber physical systems and Internet of Things. So just to set the stage, I want to say three things about the internet that are important. And then particularly we think of the internet as a thing, a single thing, but really it's a conglomerate of a lot of different networks interconnected to one another. And a lot of its key functionality resides in the computers that connect to it. So I call this sort of the rise of the stupid network. If you think about the history of networks like the telephony network, we sort of think of, Ma Bell, AT&T, this smartphone network with all sorts of services embedded deeply in the infrastructure controlled by one or a small set of companies, and the terminals that connect to the network being largely dumb, simple telephones. And yet the internet is exactly the opposite. It was designed in some ways a reaction against that, to put the hands of innovation in the people that connect to the network by allowing smart devices, programmable computers, to be connected to the network and the main functionality of the network to be dictated by the things that run on those computers rather than on the infrastructure on the inside. And this is not just higher level applications like BitTorrent or the web, but even lower level mechanisms that determine how the network itself functions are actually implemented in the operating systems of all the computers, including this one, that are connected to the net. So just to give you a sense of that, the thing the actual inside of the internet does is actually remarkably basic. It delivers data as a packet. Think of a packet as an envelope with a letter inside, a small amount of data, not an entire email message, not an entire web download, just a portion of that information. And that packet is going to be thrown into the network, and it may or may not come out the other end. It may get there, it may be corrupted, it may be dropped, it may be arbitrarily delayed, it may arrive out of order relative to other such packets that are sent by the same computer to the same other computer. So basically, the network promises to try its best to do something, and it's completely free to punt on all the basic properties you might think a network should actually offer. So of course, this is not acceptable. You want your email messages to arrive in order in a timely fashion and with the words in order and not corrupted. And so all of the functionality that makes that happen is implemented in the operating system of your computer. The packets are tagged with what order they belong in. If they're corrupted, that's detected and they're sent again. The receiver puts them back in order. And even very basic things about whether the network is congested or not are determined by the end host computers. So if my communication is going slowly, a lot of data is not getting delivered because it's contending for resources with yours, we'll both voluntarily back off and send a little bit less aggressively out of the goodness of our hearts in order to share the available resources fairly amongst ourselves. So even the fact that the network can actually carry traffic efficiently is determined by the distributed set of operations all of our machines connected to it are doing. And so you can immediately imagine now some of the security and other kinds of risks that can entail, because now my machine does, if it's a programmable device, it runs the code I tell it to run. Even the operating system, if it's open source, I can change it. I can decide to be more aggressive than you. I can send packets you don't want. I can even forge the from address in my packets so that I can send packets that look like they came from someone else. So this very emphasis on the end-host computer that allowed programmable devices in the hands of the masses to create all sorts of innovative services and mechanisms is exactly why it's possible for greed and malice to so easily infiltrate the internet, and we've seen that. So to kind of elevate those points, the idea of the internet, some of its very basic tenets from the early days, one of them is called the end-to-end principle, which is any functionality that was really necessary, if at all possible, should be implemented at the ends of the communication, not on the inside. And the second is that these devices are programmable. And so since they're programmable, it becomes possible for new services to be added by anyone at any time. And that's really, those two ideas are really so key to why the internet is an engine of innovation and able to support a wide range of services over a wide range of communication media beyond what was envisioned 40 plus years ago when it was first designed. And so, but this is really, as I was saying, a double-edged sword. It democratizes innovation, but it also democratizes risk at the same time. The second idea, which is a little more obscure, kind of now I'm going to zoom into the inside of the network. All I've said so far is that it's dumb, but it's dumb in an interesting way, which is that it's actually not a single network. It's a network of networks, and around 50,000 of them exist today. This is Princeton, Sprint, China Telecom, France Telecom, and so on, a mix of internet service providers, content providers, and enterprise networks like university campuses and corporations. And so your data going from one end of the internet to the other may go through this competitive cooperation of as many as a half dozen or more different networks to get your data from one point to another. And this is now going through networks that are business competitors with one another in different nation states with different laws and all sorts of different stakeholders with different values. And so we've seen a ton of examples by accident and by malice of abuse of this internal infrastructure that does the routing of traffic from one end of the internet to the other. And I'll just give a couple of anecdotes there. There was an incident in Pakistan where there was an order in Pakistan to censor access to YouTube because of some deemed to be offensive videos that were available through YouTube. The mechanism that was used by Pakistan Telecom to do that censorship involved, by accident, global censorship. They announced to the entire world, the best way to get to YouTube is to come through us. And then they dropped everything that came to them that was destined to YouTube. The intent was to use that as a mechanism to suck traffic from within Pakistan to a particular place where it could be dropped, but instead it ended up causing global censorship. So for 2 hours, you could not watch videos of cats flushing toilets. Okay, this is serious. So YouTube was offline for 2 hours, the entire of YouTube. And it took a global effort of network administrators communicating over email lists to coordinate with one another to get YouTube back online, to block the incorrect information that was coming out of that one ISP. A few years later, China Telecom, whether by accident or not, inadvertently told part of the internet it was the best way to reach 10% of the entire internet, and simultaneously told the rest of the world, gee, I want to know how to reach the rest of the internet. And it became sort of a man-in-the-middle attack. Attack is a dangerous word to use here because it's not clear it was intentional, but essentially for 10% of the internet, the traffic went through China Telecom and back out to the legitimate destination. So traffic was delivered, but traffic between two endpoints in the US could have been routed through China Telecom, and the user would continue to get service, degraded because it's going halfway around the world, and back again, but going through China Telecom where it would have been subject to whatever censorship, wiretapping, or other operations that might have been done there. And so those are just two anecdotes. In both of those cases, potentially by accident, but they give an indication of how local actions in a single one of these 50,000 networks can have very big global consequences because of the very nature of this competitive cooperation of networks to work together to deliver their traffic. Another thing that's peculiar about this is anyone can choose who they connect to. You can pick to use AT&T as your provider or Comcast or someone else. And so we don't even know the basic structure of the internet in any particular way. AS5, Autonomous System 5 in this picture is connected to 4 and 7. We don't even know that. There's no registry that says what the topology, the interconnectivity of the internet is. It's an actual research activity that people like us take part in to infer that kind of information because it's not publicly known. So it's an infrastructure that's critical infrastructure, and yet it's not designed, it's accreted. by the individual decisions of a lot of parties acting. And so this federated system, I talked a little bit about what's called routing. How does the traffic get from here to there? There's a whole set of similar stories around naming. How do we go from a name like www.cnn.com to a numerical address that computers understand? That too is a federated system of a ton of different computers run by different countries and different companies. There I'll give an anecdote also. Online gambling is illegal in the US, not illegal in Canada. There's a company called Bodog. If you have a computer with you, go to bodog.com, bodog.com. You'll see a very ominous warning from the US government telling you that you shouldn't be going to this site. It's actually a Canadian site, and it's blocked in Canada as well, because the part of the domain name system that's responsible for translating that name into a numerical address is run by an American company subject to US law. And so that site is blocked globally because of US law. So these are just a couple of examples of, whether you call it malice or just differences in values that have led to a lot of consternation about how we even reason about the internet as a single organization. And I'll just sort of close here by saying that we have another issue, that everything here is open. This is, again, the beauty of the internet. Open standards, all the technology that underlies the internet is specified in standards documents, implemented in open source software that you can freely download and extend. And unfortunately, a lot of these technologies were designed in a naive era when it comes to security. The perception was that the real risk was physical attack. The internet is remarkably good at having physical portions of its infrastructure go offline unexpectedly, and the network dynamically adapts to those failures. But the idea that the threat would be a cyber threat, not a physical one, was really not part of the original thinking. The good guys were on the inside, the bad guys were on the outside. And of course, now everybody's inside. And Nick will talk more about that. But I'll end just by saying a few words about an example of physical attack and the effect it did have on the internet, which is what happened on 9/11. I was involved in a National Research Council study about how the internet fared on 9/11. And it's important to note that the internet was not the object of the attack in any way. So we shouldn't view how well the internet handled 9/11 as a sign that things are fine. And in fact, it actually pointed out some really interesting effects that were pretty subtle. First, the positive ones. The internet sustained substantial growth in traffic to certain sites. The CNN website had a 2,500% increase in traffic on 9/11. There was a 1,300% growth in cell phone demand. And in particular, the internet was really useful both for getting information out quickly and for people to get word out about the fact that they were safe. We had a very long set of discussions with the person that ran the CNN website that day. And they did a number of really interesting things to make the CNN website continue to deliver information to as many people as possible. I mentioned earlier that the network divides the traffic into these little packets of data that get delivered independently. And it gets more expensive the more of those packets you have to send. So the CNN website miniaturized, if you will, the content on its homepage to fit in one packet, literally editing words down to the point that there were enough letters, just enough letters that would fit in a single packet of data, so they could satisfy more people's need to get really basic information about what was happening that day. Every other server in the Turner network of applications was repurposed to host CNN, except for the Cartoon Network, which was kept online so people could send their kids to watch something else. And by the end of the day, they had enlisted commercial services to help them scale even further, and that happened within just a few hours of the attack. So this is a real testimony to how adaptive the network can be to a really abrupt change in what resources are available or what demands are placed. An interesting anecdote from my perspective, as someone who thinks a lot about internet routing, is the internet was more stable as an infrastructure on 9/11 than on a typical day. Parts of the internet were destroyed, particularly in Manhattan, so this seems counterintuitive. Network operators, like all the rest of us, went home and didn't tinker with the network. There was no unnecessary reconfiguration of the network. There were no unintentional mistakes in reconfiguring the network. And so ironically, the network was actually in better hands that day than on an average day, which is a little counterintuitive. On the negative side, there were some interesting dependencies that people didn't know about that were uncovered. The place most affected in the sense of the internet on 9/11 was South Africa, because the directory, the domain name system, that translates human readable names like CNN.com into IP addresses, the domain name system for everything in South Africa was located in Manhattan. run by an NGO for historical reasons. That server was destroyed when the towers fell, and so it became impossible to translate any name ending in .za to an IP address. So intra-South Africa communication was essentially brought to a standstill at that time. Similarly, there was an ISP, a service provider in Florida, that authenticated its users using a machine in Manhattan. So the users and the network were all fine. They were in Florida, but they couldn't authenticate to log into their accounts because the server for that was located in New York. And finally, there was a lot of decisions made about disaster planning and co-location of facilities that were a problem that day. In particular, a lot of internet service providers meet to peer with one another, to exchange traffic with one another at co-location hotels that are located in a single place. They share facilities to make it cheaper to interconnect with one another. Some of those were damaged or destroyed during 9/11, having a correlated failure in a few places. Phone lines were blocked. A lot of network operators trying to get things back online couldn't coordinate because they couldn't get through on the phone. And a particularly interesting anecdote is there were a number of backup generators for network equipment in Manhattan that ran out of fuel a few days after 9/11 because they were not granted access to the Holland Tunnel for non-critical services, and the internet was viewed as non-critical, legally speaking, and so the fuel trucks were unable to go through the tunnel to refuel the backup generators. So 3 days after 9/11, there was a second series of internet outages in Manhattan when equipment around the lower Manhattan ran out of fuel. That's a perfect example of how the internet became critical while we weren't paying attention. So I'll stop here. I mean, the key point I want to end with before transitioning to Nick is these are all interesting anecdotes, I think, but they're in some ways just the tip of the iceberg because the internet wasn't the object of attack that day, far from it. Perhaps the more interesting point is how does the internet fare when adversaries are actually intending to harm the internet? And I'll let Nick take over.
Great.
On that.
Thanks. You set up the context very well, and in particular, this is a great segue to talk about attacks. There are a couple themes that I want to touch on from your comments as well. But first, I assume that many of you read the New York Times, and if you do, it might have been hard to miss this particular article from a couple weeks ago. It's on A1, hackers basically taking down big parts of the internet, as the headline indicates. So what I want to do is talk a little bit about what happened there. And also a little bit about why it happened, coming back to some of the themes that Jen spoke about, in particular, what is this double-edged sword of openness that we see, and what price do we pay for that? What do we pay, what kind of price do we pay, or what risks come up due to federation? And finally, what sort of risks may lie beneath the surface because of dependencies that various internet systems have on other systems? Jen spent a lot of time talking about the domain name system and this particular attack related to that in quite an interesting way. So I want to unpack that a little bit. So for those of you who weren't paying attention that particular day, which happened to be the same day that CITB was having a conference on security of the Internet of Things, this was basically going on during that conference for a large portion of the day. And if you happen to be there and we're trying to tweet things about the conference, you might have noticed that Twitter was down. You might have also noticed that Reddit was down, and a number of other sites as well. Some significant number of very large sites went offline for a better part of October 21st, 2016. A couple of interesting things there. One, so what's this title about? Let me, I assume you can read French, so I'll go to the second part of the title. So IoT, what's IoT? Well, Internet of Things, obviously. What does Internet of Things mean? That comes to actually Jen's first point about openness. One of the things that's made the internet so cool is its openness. Anybody can connect a device to the internet. All you need is something that speaks the protocols that Jen was talking about. This is cool. I can connect thermostat to the internet. I can connect my toaster. I can connect DVR cameras, as was the case here. But there's another twist to that, which is that the same openness that brings us this ease of connecting lots and lots of things to the internet makes it very easy to connect insecure devices that may be recruited into what are called botnets. So for those of you who haven't heard that term, a botnet is basically an army, if you will, a virtual army of anywhere from tens of thousands to millions of internet-connected endpoints. Historically, these have been laptops and desktops and other things running Windows typically, that basically get recruited under the command and control of a single attacker. So now an attacker basically wants to send spam or launch a phishing attack or launch send a ton of traffic at a site to try to take it down. And that attacker has a million machines at his or her disposal that can do the bidding of that command and control. So the same openness that made it so easy to connect all these things to the internet has also made it very easy to connect insecure things to the internet. And on the other side, what was the target of this attack? I'll talk about that in just a minute. The targets also are connected to this open internet, and they're happy to talk to anybody, right? So all of a sudden you have a target that happens to be critical, right, that's receiving a ton of attack traffic, and there's no easy way to basically say, no, I don't want that traffic. Please stop sending it. Okay, so that's sort of the gist and the sort of double-edged sword of openness. But another twist to this particular attack that made it so interesting was that how did it bring down all these websites? First of all, it generated 1.2 terabits per second of attack traffic. So for those of you who don't know tera, that comes after giga, which comes after mega, which comes after kila. So it's a lot of traffic. But 1.2 terabits per second, that's a lot of traffic. But it brought down a ton of sites. And the key here actually was that the attack traffic wasn't headed towards the sites. It was actually headed towards a DNS provider. So there was a single DNS service provider. They're called Dyn. You probably haven't heard of them unless you read the articles about this attack. But a lot of these websites, Twitter, Reddit, etc., they actually outsource the service that maps the name twitter.com to the IP address of the website. And this service, Dyn, that was basically running the mappings of these names to internet addresses for all these sites, came under attack. And this is actually off the blog post that the Dyn folks wrote sort of right after the attack. And I've highlighted a few things here that are interesting and relate to some of what Jen had been saying about openness. One of them, it can be difficult to distinguish legitimate traffic from attack traffic, right? So that sounds kind of counterintuitive. You're under attack. Obviously, you should know that the attack traffic's coming, right? But picture now you've got, in this case, it was tens of thousands of compromised DVR, internet-connected DVR cameras sending a couple DNS lookups, right? A couple of these name lookups, like, can you tell me the address of twitter.com? And from any individual IP address, that looks fine, right? That's normal. Any of us would do that. But now you multiply it by tens of thousands, or in a worst case, we might see millions, and now you've got a major attack. So that was one thing. Is the double-edged sword of openness comes up again. The fact that basically a lot of these services that we have come to know and love and depend on, all depending on a single DNS resolution service. Also a point that Jen brought up with regard to hidden dependencies that sort of comes out here again. Another thing that's interesting here is that some of the things that are like put in place to the very things that are engineered to increase the system's resilience actually made the attack worse. So as these servers were becoming slow to respond to requests, there are legitimate people wanting to resolve Twitter.com, right? You and I, right? We're trying to post stuff from our incredibly awesome CITB conference. And we're not, our DNS lookups are failing as well. So what do our clients do? Well, if we get a failure, we retry, right? That's good engineering, right? This is meant to add resilience, except when the site's down and when the service is down and not responding, these retries are just failing and retrying, failing and retrying. That's just adding to the attack traffic. So the very things in the protocol design that were intended to make this more resilient actually amplified the attack. So I think this is an interesting case study, and I want to talk a little bit about just IoT security in general, because I think the openness and the ability of to connect some of these devices to the internet really, again, Jen said none of the things she talked about were intentional. This was actually a pretty small scale attack. I think there were something like 30,000 DVR cameras, right? It wasn't a huge number. There have been botnets of 1 million, right? So if someone had the opportunity or desire to compromise many, many more of these devices, that opportunity certainly exists. So I think we basically have we have a little bit of a storm brewing here, because there are all kinds of things that are being connected to the network, right? Here are some examples. Sarthik Grover is a PhD student in computer science here. Connected all of these things and just to sort of watch what they did. So that those are some examples of things that you can connect to your network. I was talking with someone yesterday who runs an IoT blog. Like she was doing a firmware upgrade to her internet-connected microwave oven using the display that we usually just enter time on. So all kinds of things, people connecting to the network now. And if that's your interface, imagine what software updates look like. And now even in the best case, there have been attacks. So this kind of goes back to no one's attacking intentionally, right? But someone basically had an internet-connected light bulb that was doing over-aggressive, broadcast, universal plug-and-play discovery, and it wasn't apparently finding what it was looking for. So it was just shouting across the person's home network, and was sending so much traffic that it basically just took his entire home network, offline. So what's going on here? We've got lots and lots of manufacturers, lots of small startups, often novice or no programmers. Sometimes it's like, oh, we've got a consumer electronics company. They make photo frames. Oh, cool. Let's put Linux on that, and let's put a web server, and then let's connect it to the internet, and then we can send like photos to that over the internet, and that's cool. Except now everyone else can do whatever they want with it too. A lot of the data basically going to the cloud. That also exposes. That's another set of hidden vulnerabilities that we haven't talked about a lot yet. But the cloud is a fancy word for someone else's computer that's not yours. And there are lots and lots of data leaks that have occurred from IoT devices that send data to other people's computers. So lots of security risks. Devices, many devices that are basically difficult or impossible to patch. You plug something in and it's not necessarily isolated from anything else you've plugged into the network. So you may love Google and their privacy policy and the Nest thermostat that you just bought, but what about the Pixar photo frame that you just plugged in right next to it? Or what about that thing that you just bought off of eBay that was manufactured in Shenzhen and who knows what firmware running on it? Not that backdoors would ever be put in firmware, but of course they have been. So this is another example of something that we saw, and this should certainly give us pause, right? Because we've got all kinds of devices. Like, we don't really understand what's going on in this thing, and it's so easy to connect it to the internet. So that kind of brings me to sort of, what should we do next? Like, what are the recommendations? Like, how do we manage the risks that some of these principles have introduced? One of the things I want to touch on briefly before I get to specifics is another thing Jen mentioned was federation, right? There are many stakeholders. She talked about the tens of thousands of autonomous systems, and this is another example of an ecosystem with many stakeholders. Whose responsibility is it to fix this, right? Is it the consumers? Is it basically that we should be patching these things before we connect them? We know how well that's worked out for laptops. Is it the vendors or the device manufacturers. I mean, maybe that works if the manufacturer is Google and they have a huge army of software developers and people who know something about security. But if it's the toaster manufacturer who decided Linux was cool and just started sending these things out to Home Depot and Lowe's, then who do you go to when you need the thing patched? So another report I think that was just released last week, that was linked from the announcement for this talk, comes to some of these recommendations for a little bit kind of I would say almost motherhood and apple pie. And some of the harder questions here are, great, who should be responsible for making sure this happens, right? Obviously, we want a lot of the things that are mentioned on this slide. And now I think the question is, whose responsibility is it to enforce these or design these into the network? And as computer scientists, I'm going to close in a couple minutes talking about where I think as computer scientists we can think about what we should do in the network to improve the resilience of the network in the face of some of the things that we're connecting to it. There are lots of people thinking about how to basically do things to improve the resilience of the network in the face of these devices that are being connected. Industry is trying to do things like certification processes, et cetera, solving the problem hopefully before the regulator gets there. But regulation is certainly another thing that comes up. Interestingly enough, this is a consumer protection issue, but the FTC happens not to have recall authority. So simply recalling a device because it has insecure firmware is not actually an option. Fines are an option. Other types of recourse may be options.
So they have recall if it's physically a dangerous product,
right,
but not if it's has bad software.
Exactly.
Oh, interesting.
So lots of global threats, and I think coming full circle, we sort of talked about we started off talking about the network, right? And since we want to talk about network resilience in the discussion today, my last couple of thoughts are: could the network itself, which has been so great for innovation and now so tenuous for resilience, could it be part of the solution? Some of the things we're thinking about now are, let's just assume that people are going to connect junk to the network, right? And let's just deal with it. Software security has been a lost cause for a long time. It's even more of a lost cause when you're plugging in software devices manufactured by companies that don't have software developers. So this is hopeless, right? But maybe the network can help out, right? There are a lot of things I think basically, if one could imagine before or as I'm plugging stuff into my network and I have no idea what this thing does and I have no idea what my thermostat or toaster or oven does or whether or not my DVR camera is going to be part of the next Mirai botnet attack, could I plug something else in front of it that I don't really have to know what it does, but it's going to automatically tell me what's connected to the network. And by the way, if something weird is happening with that device, like, hey, that DVR camera that's only supposed to be talking to Nest or XM or whoever the manufacturer is, suddenly is starting to talk to thousands of internet destinations. That's a little weird. Maybe we should do something about that. So final thoughts. Internet redesign has been sort of a, I guess, almost hackneyed term over the last 10 years, but I think that's been, hackneyed in the sense of we're not going to throw it all out and start over, obviously. There have been certainly discussions about that, but I think we're well past that point. And I think one of the things that came out of those, the last 10 years of those kinds of discussions was not, let's throw out the internet and do it all over again, but if we could, what would we do differently? And I think that's been a really helpful discussion that the computer science and networking community has had over the last 10 years is, maybe there's some things we would do differently. Like maybe we shouldn't just like blindly accept traffic from IP addresses, that say they're coming from IP addresses without like testing that, right? Maybe IP addresses could have some sort of cryptographic self-certification. Maybe there should be a way for Dyn, who's coming under attack, to send shut-up packets to DVR cameras that are talking to it and say, no, thank you, I would rather not hear from you for the next N hours. These types of things are a little bit blue sky, but like due to things like software-defined networking, things that Jen has been working on for many years as well, suddenly make some of these ideas that people have been talking about not so crazy. And I think some of the things that other folks have been doing in the software-defined networking community, as far as trying to figure out, like, can we formally verify that the configuration I'm about to deploy is okay? That's becoming a reality, as well as some of the things that Jen talked about at the beginning. Like, I can't even figure out, like, what traffic is on my network, right? That's shockingly sad and ridiculous, but I think now we're at the point where we can start to ask those kinds of questions that should lead us towards a more resilient network. So those are my comments, and I think, what, Q&A happens next? Thanks.
So we've been studying this from systemic risk. This is for 3 years now, and so this was a very interesting talk for us because we think of things in terms of networks and network design. So I'm picturing, as you both lay out first the architecture and then sort of the dynamics of the network, I'm picturing these network designs where you see nodes and arcs, and they're sometimes visualized so that you can see which nodes are experiencing the most traffic and where the heavy arcs are. Who is responsible for making sure that there's sort of a safe, that's safe's not the right word, but a resilient distribution of traffic? So you mentioned Dyn as this node, if I'm thinking of it correctly, is a node in this network that just had a lot of traffic flowing through it. And is there somebody who has possibly a conflict of interest to push more traffic through certain nodes to the point where it makes the network fragile? Is it in the best interest of some people to have a more equitable distribution of traffic?
So I think one challenge here is that there's nobody in charge, and even getting the traffic from one of these DVR cameras to Dyn, the traffic went through many different networks and looked completely, as Nick said, legitimate. So if you can't tell the wheat from the chaff, it's really hard for any point along the way to deal with it. And you're right also, some of them are getting paid to deliver traffic, so it's a question of, do they have an incentive? But even if they did have an incentive, they might not have the means to actually identify whether the traffic was bogus or not. I don't know if you're getting at security risk. Some of the things you said started to hint at questions about net neutrality also. I'm not sure if you were trying to go there or not, but certainly questions about preferential treatment of traffic that are interesting here too, because some stakeholders may very much prefer some traffic to have a better experience than other. Comcast would certainly prefer that I get my cable TV from them rather than rely on Netflix, and might not be appropriately incentivized to give me good service for Netflix. So there's a lot of economic tension there as well.
Just following up, what it sounds like, if translating it into social science terms, is that this is one phenomenon that is absolutely, totally ruled by rules of the market. There's absolutely no governance. There's absolutely no regulation. It's the Adam Smithian, if enough people are doing it, it's going to come out okay. Is that?
I think that's fair. I mean, I'll give an anecdote. I've done some work with the FCC on routing security, because some of the things like the China Telecom and Pakistan Telecom attacks happen because of, the horses out of the barn. We have these technologies deployed that don't have a security mechanism. We do know better solutions, but getting them incrementally deployed in a multi-stakeholder setting is really hard. And so just thinking what the FCC tried to do in our working group was just get all of the American service providers to agree to basic security best practices. That was like a 2-year effort with the threat of prospective regulation, driving their willingness to agree to adopt that. And the idea there was, the FCC doesn't have any purview over Google and Apple and so on because they're not service providers, but they're important parties here, but hopefully they'll go along. And the international providers have no role with the FCC at all, but the hope is you get the ball rolling. And so it's very challenging. To the extent there is governance, it's often hampered by old divisions of labor, if you will, about who's responsible. Even
Yeah.
Nick's point, I think, about, which I didn't know before, that the FTC can't recall a device due to a software bug.
They actually
I mean,
don't. The
yeah.
FTC
I mean,
the FTC Act provides no recall authority. Period.
Yeah,
So
okay.
other agencies can recall, airbags or whatever. Whoever
Yeah.
does, if that's transportation or whoever. Other agencies and departments have recall authority, but the FTC Act provides no recall authority.
Interesting. So there's some
Yeah.
recourse in some cases, but it's factored in ways that make it very difficult to be effective, I
Right.
guess, if that
Yeah.
makes sense.
And I'll just shut up. But
Yeah.
one of the things, the two words that keep coming up in all these systemic risk is cascade effects and contagion.
Yeah.
And if I'm interpreting it right, there is no way of quarantining on the internet. I mean, let's say with Ebola, you say, okay, people from this zone are not allowed out of that zone. Is there an equivalent for that where some central authority, whether for ill or for good or for ill, identifies a lot of bad stuff that's coming out of zone X? We're not going to allow any traffic from zone X. Can that be done?
So it's
Or-
interesting you mentioned that, because I mean, an anecdote I've heard from a security colleague of mine who's worked a lot on the Great Firewall of China. So, China obviously has very significant censorship in place compared to a lot of other countries. There is some anecdotal evidence that exists in part to be able to block attacks. And so it's an interesting irony that some of the infrastructure you would use to detect unwanted traffic that is undesirable politically might also be useful for detecting and blocking unwanted attack traffic. So I think that I don't know if you would agree with that, but I
Yeah.
think it's sort of, so there are examples like that, and certainly individual organizations have, gateways, like Nick mentioned and suggested at the end of his talk, where they may block things coming in, but it still relies on having some ability to tell the good from the evil.
Yeah. One of
And
the
that's
yeah.
the part that's particularly difficult
Yeah.
to address.
I think one thing that Jen alludes to there, which is important to amplify, is the prospect for collateral damage is just like massive, because it's really hard to separate the legitimate traffic from the attack traffic. One of the things, like in that botnet, the DVR camera bot, that's called a distributed denial of service attack, and the key word there is distributed. So if it was coming from just one place or just one country or just one region, then you could be like, well, I don't want to talk to that.
Yeah.
But when it's coming from 50,000, and by the way, they're not in the same place, and by the way, they might be actually on networks that also have legitimate stuff, right? So you can say, I don't want to talk to that network, and then you've cut off a bunch of legitimate people.
And they're sending one or two packets,
Yeah.
so they don't even look that
Yeah.
bad individually.
Yeah. Another example where that kind of collateral has shown up is in spam filtering. So, to your point, blacklisting is a common thing that's used for defending against certain kinds of attacks. So, if you're getting a lot of spam, one of the things people used to do before botnets was say, "Oh, it's coming from that address. I'm going to put it on a blacklist." Well, what happens when that machine gets compromised and starts sending spam, right? So if it's the Princeton mail server, right, or what have you, and suddenly a bunch of spam starts coming off that machine and someone blacklists it, which, by the way, not to Princeton, but by the way, that has happened to many legitimate mail servers. Now suddenly everyone at Princeton or whatever, they can't send email to people because all the emails showing up in people's spam folders. So it's very, very hard to say, I don't want to talk to that, because it's often commingled with other things that you do want to talk to.
Why do these attacks happen? Are they people who have some sort of reason that they want some part of the internet to go down, or are they people who are just experimenting and want to try see how many problems they can cause?
It's a mix. I think some
it
I don't know
varies,
about the
yeah.
most recent one, you probably know better, but some denial of service attacks are actually extortion of sorts, like, pay me, or I'm, in a Swiss bank account, or I'm going to do X tomorrow. Some of them are retaliatory in some way, and I think, I don't know, in the case of the recent attack, is it known what the motive was?
In this one, I'm not sure. So the one that immediately preceded it was against Krebs, Brian Krebs, who's a columnist on security, right? Who'd been writing a lot about this stuff. So his website came under attack, also from the same Mirai botnet. It wasn't clear to me what the motive was for the attacks on Dyn, in this kit, to bring down these sites, but that one had a clear target. Sometimes it's that. I think another example that some of the folks in this room know quite a bit about is there was a denial of service attack against GitHub because they were hosting open source software from a group called Great Fire. to circumvent the Chinese firewall. So China didn't like that very much, so they basically just sent a bunch of traffic at GitHub, taking pretty much all of GitHub down, right? So,
interesting.
So that was so it could be politically motivated attackers, financially motivated, could be bored. What was the
Script
phrase?
kiddies.
Yeah, the script, or the 400-pound person on a couch or whatever it was. Yeah,
Yeah, exactly.
yeah.
And in some of the incidents I talked about, they were potentially accidental, right? You know, like the Pakistan Telecom one was a good example where it was intentional local censorship, but the global censorship was a configuration mistake. About half of the outages on the internet are accidental, caused by human error, because a lot of things still manually configured. So I think I wouldn't underestimate the accidental side of things too.
But they're more often motivated as opposed to just for fun.
Hard to say, I guess.
I don't know the breakdown.
I don't know either. The early ones were kind of an experiment. I guess some history might be appropriate here too. Like the first internet worm was in 1989, actually. Robert Morris, son of the chief scientist at the NSA, ironically enough, right, decided he was going to experiment with self-replicating code, right? Like basically a program that could replicate itself and spread across machines. And as the story goes, that was basically experimentation. He was a graduate student in computer science. The only problem was the code was so aggressive in trying to find other vulnerable hosts that it started to consume too many resources on the machines that it was running on. It ended up taking down about 10% of the internet at the time, which was, I don't know, a few hundred hosts at the time, right? But so that was a sort of experiment gone awry.
And there's certainly a lot of financially motivated, spam and phishing attacks are clearly more financially financially motivated.
Absolutely.
Regarding the attack on Dine, I recollect that days or maybe like a week or two prior to that, there was in the news an announcement that they were centralizing or updating the DNS mechanism they took it out of the hands of the United States. Coincidence or what?
Probably coincidence.
Yeah,
I think that's been years in the making, and I wanted to mention that too.
What were they? I didn't pay much attention at the time.
So it's a little bit of a separate issue from so Dyn is basically implementing protocols that do the lookups themselves. And that process which you read about that was centralized is actually a process by which the names are given out, by which the organizations can get a name. So that's still run by an organization called ICANN, something Internet
Corporation for Assigned Names and Numbers. It's a pretty sexy name.
Yeah. Which I guess was sort of under the purview of the U.S. for quite some time, and there's been a process of handing that off to a multi-stakeholder governance model, but they're not really involved in the running of this particular infrastructure. It's more of a governance issue of who gets the names, and can we have a new top level, .Feamster domain or something?
Elvis,
right, exactly. So they're making those kinds of decisions. But yeah, it's an interesting point because when Miguel was asking the question about centralization, there are certain things in the internet that are centralized, such as the naming and addressing allocation. And another one, you mentioned routing security. So there's been, I think, really interesting work there too. Sharon Goldberg and others have done some really interesting work. You'd think securing the routing protocols that Jen was talking about would just make the internet more secure, right? And more resilient, except the processes by which we secure things often involve centralization of key distribution, right? How do you get security? You have a bunch of keys, right? And people sign things with keys, and who gives out the keys? Well, typically those distribution mechanisms in the infrastructure is centralized. Who gets to control the infrastructure? What if it's, by the way, someone who decides that they want to take YouTube offline? Well, now it just got really easy, because all they have to do is make the signatures invalid.
Yeah, and my FCC committee on internet routing security got completely hampered on this because you need a root of trust. And is the root of trust supposed to be in the US, or is it supposed to be the UN or the ITU? And a lot of people were uncomfortable. Everybody was uncomfortable with at least one of those answers.
Yeah.
I was going to ask a question about what you mentioned about the attack in Pakistan. where they conducted an attack by basically asking people to route traffic to YouTube through servers?
Through Pakistan Telecom. They essentially told their neighbor, all the networks they connected to, that they were the best way to get to the addresses that correspond to YouTube.
Is the flow of internet traffic based on self-reported performance metrics or whatever they are?
It's self-reported, but not even performance. So you're being too generous. No, basically what happens is Princeton will tell its immediate neighbors, this is a block of numerical addresses that I can reach, and they'll in turn send traffic in the reverse direction to Princeton. Those networks will in turn tell their neighbors. So it really does spread, like contagion is not a bad word for it. It really is a diffusion from one neighbor to another. And so 6 hops away, you're getting information from someone you trust who might have gotten information that they thought they could trust. And now you're in a position of not being able to judge the veracity of the information. And that's what happened here.
There's no authority to ensure what providers are saying about their own abilities.
So this is exactly what my FCC committee was about, is that the technology was deployed without any of those assurances because it was built on a presumption of trust, and now we've got a problem that the horse is out of the barn. Yeah. And it's very difficult to retrofit now because you've got to get 50,000 parties in different countries with different financial interests to agree on a technology and agree on a deployment strategy and agree on a cryptographic root of trust and what government or non-government organization will run it. And so you just get wrapped around the axle very quickly because of those things.
This point actually reminded me of something else, because we talked about openness as far as like connecting hosts to the internet and like how easy that is. Another thing that you're talking about here is how easy it is for one of these independently operated networks to just like pop up like a weed basically and connect to other networks, right? And of course, as you just alluded to, if the person who you're directly connecting to, there's some kind of trust or something there, right? But actually there's other stuff going on there too. Let's suppose you're a scammer or someone who wants to like launch attacks and you've got a network and you want to connect it. Well, there are not so scrupulous independently operated networks. They're called bulletproof hosting networks. And there's one called the, I think they used to have a Wikipedia page. They're called the Russian Business Network. I
want to work with that.
Yeah, exactly. In fact, it sounds like one network, but in fact, just like the internet, it's not one network. It's like thousands of these like weed type networks that pop up. And what happens is one pops up and like suddenly it's hosting lots of bad stuff like denial of service attack and spam and scams. And okay, now we go try to shut it down, or we say we don't want to talk to that one. No problem, they just come back as someone else. And actually some of these bulletproof hosting organizations make big money from the spammers and scammers, because that's big business, right? And they're willing to pay to be like, well, let me connect over here and then let me reconnect over here. And if you've got if you're the Russian Business Network with 1,000 intermediate points, such that if you just pop up over here and then they accept you and then the rest of the internet just believes you, then this just got really hard.
Yeah. So this sounds all very negative, and I think it is in a way, but I think there are some, particularly your question, right? I think there is a path forward. I mean, some of it relates to the sort of heavy lifting of working with regulators to try to identify best practices and either get voluntary or force adoption of them. And I do think that's a piece of it. There's also a bunch of creative work going on creating economic incentives for incremental deployment. There's things the government can do, and it's something our committee looked at as well. It's like, securing the routing system involves cryptographic operations. That's computationally expensive. Some of the network equipment can't do it. But some of the router vendors that I spoke to said, if you just told the government that we need to put a crypto chip in every router, otherwise they won't buy our routers, we will do it. Yeah. Please, like the engineers in those organizations are like, don't tell my boss, but please tell the government to tell me to put that chip in, because my boss won't let me because it's wasted money if nobody wants it, but if somebody wants it, I have to put it there.
The same thing is absolutely true for the IoT devices. That exact, like a very similar discussion is ongoing with regards to that, which is that I have the 99-cent window lock, right? That's maybe I'm gonna like pay $1 for it and throw it there and forget about it. Should that thing have crypto, right? Well, crypto of course costs money. It's costing less and less, which is good news, but it still might make your dollar thing $1.50 for $2, right? And if you've got 1,000 of them, then it starts to be a cost. But this is another example of, yes, we have this in other industries. Like, yeah, airbags like increase the cost of vehicles, but we have them.
Right.
So why shouldn't we basically ask the regulators or have the industry get their act together to say, no, crypto is important, right? We can't just have things connecting willy-nilly without the ability to do, say, secure software updates.
Yeah.
So along the same lines, was DynNet able to take any action to make themselves more resilient? And also a comment, the projection is that by 2020 there are going to be 50 billion IoT devices in the network. So that's going to grow exponentially over the next 4 years.
Yeah. So Dyn actually, and this is actually another thing that is it's a theme that we haven't talked about enough, but like one of the nice things about many internet protocols is they do have the capability for redundancy built in. And Dyn had an East Coast data center and a West Coast data center. And part of the reason, like a lot of people on the East Coast were seeing the outage and not people on the West Coast. And that's because a lot of the DNS requests from the West Coast were being served out of that side of their operation. So to mitigate this attack, the first thing they did obviously was basically, send a lot of the requests over to the West Coast. So that redundancy helped. Then the West Coast started coming under attack and they basically had to do more provisioning and they were able to basically counter it through, a combination of redundancy and countermeasures such as, clever filtering. But it took about a day. Yeah.
Why do Reddit and Twitter and these big websites outsource this function to Dyn?
Probably the same reason that that's a great question, yeah. Probably the same reason that if you want to have a website, you probably don't buy a machine and go plug it in and install a web server and try to keep it up. It can be a lot more cost effective to have someone else who basically is running that service for their business do it for you. So similar kind of concept, I would say.
Yeah, and I think just to pick up on that a little more, you mentioned this too, but then now we have a bunch of websites that are all using the same domain name system provider. As I mentioned that there's a lot of internet service providers who met in the same building in Lower Manhattan, and all of them had their routers destroyed at the same time. The Baltimore Tunnel fire that occurred a number of years ago, there's a lot of internet fiber that went through the Baltimore Tunnel. A whole bunch of internet service providers relied on that fiber. So these correlated failures because of shared physical risk happen either by accident or natural disaster, but they happen also because of cyber attack, because there's economic incentives for consolidation, and they provide a very attractive target for physical and cyber attack.
Yeah, the fiber example is a really nice one. The Baltimore tunnel fire example. It reminded me of another really interesting piece of work on internet resilience by a fellow by the name of Sean Gorman. He did this. He mapped out. I don't think you can do this anymore. It's all been taken down. But he took public fiber maps from basically lots of ISPs. Used to put their fiber maps online. He took all the sort of major ISPs from the U.S. fiber maps, built a U.S. fiber map from publicly available data. And what he did was really interesting because you'd think if you want to basically, what if you did want to take down the internet? Well, you might think I'm going to go to New York and take down this huge central office or data center or what have you. And it turned out actually that the answer, place where all the fiber came in, right? And it turned out the answer was no. You actually don't want to take out the high degree node. If you're sort of looking at the network layer, if you will, where the packets are going, that'll give you one view of the network. But actually, if you go one level deeper, which is where the fiber is in the ground, physically where the network is, it's going along highways and railroads and things like that. And if you want to basically take out the internet, his conclusion was you don't go to New York, you go to some random cow place in Oklahoma where all the fiber between New York and LA is going. There's just a few places in the country where this is, where these conduits are, and you just go snip that. And by the way, no one's guarding it, as opposed to the big building in New York. So
yeah. Similarly, there's only so many ways to go through the Rocky Mountains.
Right.
I mean, they're big.
Right.
There are not that many. There are not many paths. There are not that many paths. So I think the idea of consolidating physical infrastructure that's not unique to the internet. I mean, there are particularly strong economic incentives here because it's not designed by a government.
Right.
So it may be even more of a problem with the internet, but it's not a new problem.
Yeah.
People speak a lot about SCADA attacks in the past few years.
Good point.
Do you think that government are taking enough measures to protect their infrastructures and what's going on in that aspect?
Yeah, good question.
I don't know too much about the SCADA network.
Yeah, I mean, SCADA is a protocol that's used to talk to, like electricity grids
Yep.
and nuclear plants, and so it's used in sort of these cyber physical settings where you have these devices that you need to control. I don't know a lot about it myself, but certainly there have been some pretty high-profile examples of vulnerabilities there that have been where you can drive a power plant into an unsafe mode where it actually damages the equipment, and that certainly has happened. So I think it's another example of, you talked about IoT devices as vulnerable and attacking others, but I think we haven't talked enough in this discussion about the fact that once you have an internet-connected device that affects change in the physical world, then all sorts of interesting things happen. And we've had faculty candidates come here and give video demos of a pacemaker being cyber attacked, and they can't even do the attack in the room because if anyone in the room has a pacemaker, it's game over, dude. So there's certainly examples of attacking electrical grids or patients, et cetera, and those are particularly disconcerting.
Yeah, I know less about the SCADA networks, but certainly like a lot of the points that Jen speaks to on cyber physical systems, I think those examples are sort of ripe and ready. I mean, the Nest thermostat had a buggy firmware upgrade last year that caused the battery to basically just die, which basically left a bunch of people without thermostats in the winter, resulting in frozen pipes. So there are examples like that. I think Jay Dominic here in OIT has talked about the Zigbee controlled lights on the stadium interacting in funny ways with the non-smart lights in ways that the lights are flipping on and off, and they can't even explain why at the moment. So
interesting.
So not SCADA, but certainly I think as some of these cyber physical things move to the IoT, there's definitely
there's certainly examples of people hacking cars. I mean, there was an example where a bunch of people hacked a car and drove someone off the road.
Comment on that? I was at an Intel Master Peak conference about 2 weeks ago, and one of the keynote speakers for one of the mornings was Ted Koppel. He wrote a book on SCADA attack vulnerability, and it was amazing. But he predicted, or he said basically how close we are to major issues regarding SCADA because it's not protected. He said that many foreign certain nation states are in our SCADA systems right now, and so that's something that we need to really watch out.
Yeah, and there's certainly a lot of policy questions here that are interesting. Can a military response be an appropriate response to a cyber attack? And you certainly hear a lot of discussion about that. I mean, it's definitely asymmetric warfare out there right now, and it's an interesting question what to do about it.
Yeah. I mean, I think like also to this to your point. Obviously, I think one of the more famous cyber physical attacks was the one on the Iranian centrifuge, right? Stuxnet, right? And
exactly.
That's an example of now the buzzword, of course, is this APT, right? Advanced Persistent Threat, something that basically is very, very targeted towards something like that.
A movie that just came out, a documentary called 0 Days, talks about this stuff in detail.
Yeah, so that's a really interesting example, but I think. I talked like for a second about backdoors in phones, right? So this is something I know the campus even is thinking about. Like as we buy, internet connected whatevers, who made the firmware, and can we, is there a backdoor in there? How do we even know? So yeah, things to think about.
I should say on this point about asymmetry, where the bad guys have a distributed programmable infrastructure of all the computers and devices all over the internet at their disposal, the good guys don't, and that's actually is a to whatever a good guy is in this context. But to the point on Nick's last slide is important here, that by making the network infrastructure itself more programmable, we're giving the people that are defending the infrastructure and defending the computers connected to the infrastructure at least a way to respond and to adapt their response as the adversary adapts. Because we're sort of flat-footed a lot in this setting because the adversaries are able to adapt more quickly than the defense mechanisms are.
I love the point about asymmetry. I mean, that's another sort of theme. We talked about openness, federation. Asymmetry is like a huge theme in a lot of these attacks. And also when you look at defenses that people have tried to employ, they've tried to sort of rebalance that. An example of that is denial of service. A lot of the denial of service attacks, not the one I talked about, but they use a technique called reflection or amplification. And the idea there is like the attacker sends an itty bitty packet, and that causes some other machine like that hears it to send a much bigger packet to somebody else. Right? So the attacker has to spend very little resources, and then some other reflector node is basically generating some huge packet. That's an example of asymmetry. Another example is just the standard, I can send a, hello, I want to talk to you, to Jen, and she starts allocating memory or state, right? And I just never come back. Well, it costs me nothing to do that. I can do that 1,000 times, and soon she's out of memory. So the defenses like that we often see towards these are to sort of reinstate some of the symmetry, like make it more expensive for me to send those packets, or redesign the protocol so that if I send something to her, she doesn't allocate any state before I actually do some work or come back later. So the asymmetry point is a really important one because it shows up as a theme in many, many attacks, and reinstating symmetry is an important aspect of defense.
The Stuxnet comments actually kind of reminded me of how those like zero-day exploits on Windows. And I was wondering, do you guys think like open source, specifically at the infrastructure and the system level, has kind of really helped make a dent in kind of anticipating and finding these attacks before they happen?
Boy, that's a
great question.
That's a really interesting question.
I think conventional wisdom is the open source software is better vetted, although then again, I think it's actually the vote's still out because certainly bad guys can play a role in creating the open source software as well.
Yeah, I think like Jen highlighted the conventional wisdom certainly very well. But another sort of very interesting research area is actually the security of open source software projects, right? So first of all, the reliance on open source software libraries. And Professor Mike Friedman here has started to think about exactly that problem. What happens when you build an IoT device and you bring in an open source software library, and who knows like who wrote that and whether it has vulnerabilities or a backdoor or what have you.
And that's a shared risk too if everybody's using the same piece of code.
So I don't know if people were familiar with the Heartbleed vulnerability, but that was an example of like everybody uses OpenSSL, again, something that's supposed to make us all more secure because we're using encrypted communications, except when it had a bug, right, that exposed private keys of servers, then now everybody is out of commission.
Exactly.
Yeah.
Well, I hate to scare you, but the governance structure you're talking about, the network structure, sounds eerily like the banking and finance system.
That is so
You're
right.
basically relying on I can make a loan to you because I know you, but I don't know whether you have been as careful in making loans. I mean,
it's cascade.
Yeah, that's a good point.
And on that happy note, thank you so much.
Thank you.